This Week in Radio Tech, episode 161, is made possible by Telos Systems and Axia Audio, working with industry leaders and organizations to set meaningful standards of IP audio interoperability. Visit Telos and Axia on the web at telosalliance.com.
And now, our feature presentation.
Twert.
It's the beginning of the end for ISDN. What's next for audio transmission is IP. But how do we make that reliable for broadcast?
All right, calm down. He says that to everyone.
This calls for immediate discussion.
What's up, Dad?
All your days are belong to us.
From his palatial office of important business,
or in a choice hotel in a distant land,
this is Kirk Harnack.
Tom Ray and Chris Tobin join me for a long episode of discussion and learning about IP audio reliability.
You're dialed in to This Week in Radio Tech.
Hey there, it's time for This Week in Radio Tech. I'm Kirk Harnack, your host. I'm so glad you've joined us. This is the show where sometimes we get really deep in the weeds in radio technology. And this time, on this episode, I'm delighted we're going to be talking about streaming technology again, but this time in a little more scientific light. I'll tell you more about it after we introduce the co-hosts on the show. First of all, let's bring in from the Hudson Valley of New York, my friend and yours, the inimitable Tom Ray. Hello, Tom.
Greetings and salivations. How you doing, Kirk?
I'm great. Great. Good to see you.
Excellent.
So, Tom, give me the elevator speech on what you're doing now.
Well, I'm running Tom Ray Broadcast Consulting. I've got a couple of stations who are actually contract engineering gigs. I write as technical editor for Talkers Magazine, and I've got let's see, I'm working on a couple of FCC applications and a whole bunch of other things. So I'm kind of a jack of all trade and having a great old time.
If folks want to get in touch with you, what's the best way for them to follow what you're doing?
Well, they can either follow me on Facebook or my website is www.tomrayconsulting.com, and email address is tomray@tomrayconsulting.com.
Cool. Thanks. Our other co-host with me tonight, the guy who I hope is going to badger me a little bit and get me to think out of the box, it's the best-dressed engineer in radio. Ladies and gentlemen, it's Chris Tobin. Hey, Chris. Is it just me?
I believe
I don't hear any audio from Chris.
Chris, did you mute?
Look at that. That's what happens when you hit that button on this console. Sorry about that. Yes, it's one of those days. I've been traveling around with SMPTE meetings and SBE meetings today, so it's been a little chaotic. So I'm actually at the CBS Broadcast Center here in New York City, and I'm sitting in the studio of a familiar radio personality also seen on television, the Osgood File. This is the studio where Charles Osgood does his radio show for the CBS radio network. And he says his famous line, which is, the Osgood File, I'll see you on the television come Sunday morning on CBS. And here is the cue card that he uses right here.
Wow.
So you can see
he hadn't got that memorized by now?
So this is where it's done. And the gentleman that you see in the background through the glass, that's the control room. He's the producer. Charles is on vacation this week, so I'm not filling in for him. Someone else is out of, I think, Detroit. And that's the producer back there. He's putting together the shows for tomorrow morning. So that's where I'm at. CBS Broadcast Center here in New York City. And
awesome.
I'm on a dedicated link. They're telling me I've just a speed test. I've got 6 megabits up, 6 megabits down, and the ping test was 8 milliseconds. I don't think I've ever seen it that low.
Wow.
So hopefully it holds up.
It's 8 milliseconds from here to my bedroom. That's pretty good.
So those little ping tests. And I just have to thank the folks at the CBS Radio Network, Dial Global, VP of Engineering Mitch Glider, and VP General Manager Gary Williams for making this possible. I was at a SMPTE meeting across the street at All Mobile Video regarding fiber optics 101 for broadcasting. So that's what brought me here to the CBS Center.
I'd like to know something about that. So we ought to do a show about fiber optics. Maybe you could fill us in.
Yeah, that's pretty cool. It was interesting stuff, and some of the folks I've worked with actually, they were talking about some things that we've done for broadcasts, outside broadcasts, as well as just for sonnet rings and fiber rings around town. So that's where I'm at. So when you look at the video, that's what you see. This is the Charles Osgood studio, the actual spot. I'm sitting at the chair he sits in. They were very kind enough to let me do this. It's kind of scary.
So, well, glad you're there, and Chris, I fully expect you to challenge and or complement or add to what we're talking about today. A little bit of news earlier this week. News came down this week that Verizon has stated that they're not, after May 18th, they're not going to accept any more orders for ISDN lines. And I believe that means ISDN BRI, that's basic rate interface, is the standard ISDN line with 2B channels, as opposed to an ISDN PRI, primary rate interface, that is kind of like a T1. It's got, instead of a T1 having 24, it's got 23 channels, but there's a bigger data channel, and apparently they're still going to be providing those, but no new orders after May 18th. And Tom Ray got right on the stick and wrote an article about this in Talkers Magazine. Article is called Verizon no longer taking, well, it's a repeat of the headline, no longer taking orders in the Northeast starting May 18th. Tom, give us the summation. What does this imply? What does this mean for us?
Oh, well, for broadcasters, I mean, this could have, this affects a lot of remote broadcasting. Everything from going up to the car dealership up the street to NFL broadcasts to Major League Baseball broadcasts and everything else, because in the last 20 years, we've used ISDN to shuttle from point A to point B. It's rather inexpensive. It's as easy to make a connection as a dial-up, as dialing a telephone. You don't have to call the phone company every time you need to make a connection. If you go to a different venue, you need a different ISDN line. But if you're sitting in a studio, like for example, Chris is in New York right now, you can pretty much dial the world and if the guy on the other end has an ISDN box, you're all set. This is going to impact a lot of things, and this is, I don't know if you want to call it evolution or de-evolution. We started out, when I started in this business, we had AT&T long lines for going over state lines, which were dedicated broadcast services. They went away. We picked up things like the Comrex 2-line frequency extender to get over state lines and make it sound decent. Then ISDN, actually Switch 56 and ISDN came in, and we've been using it ever since. And it gives you studio or close to studio quality audio, over 128 kilobit data circuit, and it's going to start to get interesting because, as you know, I'm also involved on the weekends with a network radio program. It's a independent syndication. Ron Ananian and the Car Doctor. He was a WOR radio network program, and we've been getting to the uplink with an IP codec with him. It's worked out rather well. It's been very stable, and but boy, I tell you, some people get the heebie-jeebies when you start saying, "Hey, I want to use an ISDN codec."
Well, and that's understandably so, and we're going to dive into exactly that subject. People get the heebie-jeebies when they say, well, wait a minute, not ISDN, I've got to use IP. Well, there's problems there, and there are, and usually they're mitigatable if you know what you're doing, and sometimes they're not. But we're going to get into that exact subject. I want to point out a couple things about ISDN, just for the audience that may not know all about it. For years and years, back up a little bit. There's two basic technologies in getting data of any kind from one place to another. And the two technologies that are widely deployed around the world are circuit-switched data and packet-switched data. Now, circuit-switched data means that when you establish a connection from point A to point B, you get a circuit that is all yours all the time. Nothing else interferes with it. There's no cloud involved. There's no mystery involved between point A and point B. It's a connection that ends up being effectively a send path and a receive path between point A and point B, and it's yours all the time. It used to be, up until the world of voice over IP, if you made a phone call almost anywhere in the world, you got a circuit, and it was all yours. And that circuit was either up or down. It was, you dialed it, it was connected until you hung that circuit up. And that applied to voice, and that applied to data services like ISDN. Then, and the other technology being packet switch data, where there is this notion of a cloud. And in the cloud, there are routers. And routers, on a packet-by-packet basis, send the data. You go over there. This packet goes over here. You go over there. Least cost routing will go over there. And so there isn't a permanent connection between point A and point B. There are lots of connections, but the data is switched on a packet-by-packet basis. So if, for example, we did not have the idea of packet switch data, then if you wanted to browse to google.com, you would have to make a phone call or run a wire from your computer to Google. And you would have that connection as long as you needed. And by the way, before the internet came along and packet switching came along, that's how different universities and research centers and military installations were connected. They had permanent connections. Typically, they may have been 56 kilobits or 32 kilobits or 64 kilobits per second, permanent up connections. And packet switching changed all that. You then just needed to have one connection to some cloud, if you will, and then the cloud would switch each packet contained the here's where I'm from, here's where I want to go to. Now send me along on the way. And so the cloud will switch the packet to where it needs to go. So there are enormous benefits to packet switching, and there are some downsides too. And so what we're going to talk about on this show is how do we mitigate those downsides when we're using packet switching for transporting real-time, low-latency audio from point A to point B over the public internet. Are we good so far? Any comments on that point?
No, you're right on spot.
No? Okay, good.
Yep, you're doing good. You're doing good.
Woo! So, somebody's gonna blow me away sometimes and say, no, Kirk, you got that all wrong. And explain how it really is. So,
well, we're just getting warmed up here. Give us a chance.
Over the years I've worked for Telos, I've been asked to explain what is ISDN. And one way that I've explained it is that, the phone company, now this is before everything became, or a lot of stuff became packet switch, with the infrastructure at the telephone companies that has existed in the 60s, 70s, 80s, 90s, and up to today. Internally, phone companies have been circuit switched. Now, they're becoming more and more packet switched in various hybrid combinations, but circuit switch is how you could think of the phone company, even dialing from one phone company to another across town or across the world. And in fact, if you had a POTS phone line, an analog phone service, the phone companies have been all digital internally for years. And to bring analog phone service to your home, they had to convert the digital into analog and bring the analog wires to your home so you could plug an analog telephone into it. All ISDN is, essentially, is taking the digital port on the phone company's big honkin' switch and extending that port out to your premises, out to your home or business or football stadium or whatever it might be. So you've got direct access to essentially the same digital infrastructure at the phone company as the phone company has when they convert it into analog to bring you an analog phone line. Now, it's not quite like that, but it's pretty close. So if you have an ISDN phone circuit coming into your business, and this gives you, in the U.S., on a pair of wires, a single pair, you have digital hash going on there, and you have a little device usually called an NT1. It's like a modem that turns that digital signal on the wire into send and receive. And if you put data into the send, ones and zeros, at the other end, you get those same ones and zeros out. So it carries the data bit for bit from wherever you are, whether you're using it for dial-up internet over ISDN, and there used to be plenty of that, or a lot of folks in broadcast, their only knowledge of ISDN is to connect two Zephyrs together, or two of anybody's ISDN codecs. Like the ones from Musicam that Chris is associated with, and there are other brands too. So those are ISDN codecs, and that's how lots of folks understand the functioning of ISDN. ISDN can also perfectly interconnect with the voice switched network, or the circuit switched voice network. You could order ISDN to be circuit switched data or circuit switched voice or both. And if you ordered it to include circuit switched voice, you could have, in fact, plenty of other countries. Like in France, they had a lot of ISDN. They still do. You can buy a telephone that's an ISDN telephone. You plug your ISDN line into it, you pick it up, and you dial somebody, and they have an analog phone, and they talk to each other just fine. So, in fact, that was the basis of a Telos product called the Telos Export. You would take it out in the field, hook it to a POTS line, make a modem call back into a Telos Extreme, hooked to an ISDN line, and the two would talk to each other. And they would convert, modem data, and thereby, pass, coded audio like AAC, coded audio between the two. So ISDN and POTS, very interchangeable. I realize one's digital, one's analog, but the phone company, it's all the same thing. It's all the same ones and zeros and the same kind of data channels. So what is great about ISDN, and you guys jump in here and correct me or add to what I'm saying, what's great about ISDN is that it's a tariffed service from the phone company. It's a known quantity. It must work the way that they advertise. Otherwise, they can't advertise it. It doesn't. If you get to an ISDN phone line and it only passes 3/4 of the data that it's supposed to, it doesn't meet the tariff, and they have to come fix it. They're legally required to offer the service working, and if they can't make it work, then they're not allowed to offer the service. So an ISDN phone line, if you order one at, let's say, the Ford dealer to go do a radio station remote broadcast in high quality with somebody's ISDN codec, when you arrive there and the ISDN line is installed, it legally has to work. And you'll plug it into your ISDN gear, and you'll have the equivalent of ISDN dial tone. You can make the call between two Zephyrs or whatever you may have, and they will talk to each other. The ISDN connection is not packetized, but it is framed. So there's framing and timing signals going on. And it was convenient for broadcasters because it supposedly it just worked. That was just like your POTS phone service. It just worked. Just like if you order a T1 service, it works in a very expected way. And that's a lot different from the world of IP. When you have an Ethernet, when you have an internet connection that ends up being Ethernet to you, the end user, and you're guaranteed best effort, or that's what they sell you, best effort. And you may buy a line that's supposed to be 10 meg down and 5 meg up, but there's all kinds of other parameters that aren't specified. How much jitter is there? How much latency is there? Between the time you send something and the time it's received. With ISDN, if you put some ones and zeros in at one end, they would come out the other end really quickly. And I'm sorry, I don't know how long that would take. Chris Tobin, do you have an idea, or Tom, any idea of what the typical latency from one end to the other of an ISDN phone call?
Depends on the algorithm.
I'm
not even talking about the algorithm. I mean just the data. You put a 1 or a 0 in one end, when does it come out the other end?
Well, Chris, maybe you'll agree or you won't, but the fastest algorithm I think for turnaround is G.722, and that comes out about a quarter second. So, I don't know. You're probably talking less than the eighth of a second to go from one end to the other.
Yeah, it's tough in a switch network to just simply say 0 in, 0 out the other end, and how fast it's going, because it's based on the clocking of the network you're in. I'm not talking about algorithms. I'm just talking the clocking for the actual 0 to go somewhere. So, but I think Tom's right. It's probably a quarter of a second less. I mean, G.722, depending on how you set it up, you're talking, I've done tests, we've had, 10, 12, 15 milliseconds from one end to the other. Yeah, but it's pretty fast.
That includes the algorithm. I'm just speaking of the transport mechanism.
You're talking just the basic, without the payload. You're just talking just the roadway, nothing else. Just
Alex in the chat room says he's tested LA to DC over ISDN 4 milliseconds, and I can believe that. It would be no longer in time, and maybe shorter than a POTS phone call. On POTS phone calls, at least within the same country, you never noticed any delay. Of course, maybe we grew up with it, but as opposed to cell phones, where there's quite a bit additional coding delay to get the data rate really down. I guess my point, ISDN is clocked by the telco. All the telcos are tied together in a clocked network. And so the clocking, between here and France, it's either mitigated or they're both fixed together. And so they're synchronized. It's not like packetized data, which is asynchronous. It's not synchronized. You can run a system to make it kind of act like it's synchronized, but in the end, it's actually not. So
right.
I'm trying to make the point that ISDN, why has it been good and convenient for broadcasters? Now, I got to point out the other side of ISDN, though. There are some people in our industry who say, well, ISDN is great, it's reliable, it's just the best thing for doing remote broadcasts. I talk to our support guys at Telos. They get calls every week, almost every day. Hey, I think my Zephyr is broken. It does this and this and this. And we'll run a test. We say, no, it's your ISDN line. Your ISDN line's not passing the bit error rate test, or it's not hooked to a long distance carrier properly.
It's not properly provisioned.
But not properly provisioned, or it's not behaving properly. So it's not like ISDN is without trouble. ISDN has plenty of trouble. I think especially nowadays when there are fewer and fewer telephone company techs that really know what ISDN is and how to make sure it works right before they leave the premises. So those who think ISDN is nearly a panacea of reliability for broadcasters, no, be on the support end of the phone calls, and you'll find out that oftentimes the answer is you got to call your ISDN provider and come out and have them do a bit error rate test or a BERT. And don't let them do it for 30 seconds. Make them stay there for 15 minutes. Buy the guy a cigarette or a cup of coffee if that's what he needs to hang around for a few minutes. But you got a problem with your ISDN provider.
Well,
unfortunately, go ahead, Chris.
Oh, I was going to say, I think, Kirk, what you're basically pointing out to everybody is that ISDN, which is actually a set of standards, so T1s are actually part of the ISDN protocols, and they're all time-based networks and stuff. I think we all have to come to realize, and I've been doing this just as well as all the rest of you, the industry, the marketplace we're in has changed and shifting. Phone companies, well, depending on who you talk to, Verizon is not a phone company; they're a communications company. AT&T is a communications company. So all of what we would expected or what we've come to enjoy, which is the 5 nines of carrier class connectivity, I'll call it. That's basically your telephone is dial tone. You never question it when you pick up the handset. ISDN, we've come to learn the same thing. We turn on our codec, we dial a number, and we go. We don't look to see if we have actual connectivity or if there's a little flashing light on the back of the box or anything's going on. We just do it. But now that we've changed the way we do business in the world of communications in the last 10 years, all these services are no longer moneymakers. So, the need to keep them going is sort of dying on the vine. If it wasn't for the tariffs in most states, you would have lost ISDN probably 10 years ago. I'm not sure what the latest one, but I'm not sure if the latest announcement with Verizon, Tom, have they made a petition to the Public Service Commission to alter it, or are they doing this new change so that because of it's new installations, they don't have to because the tariff was altered, I think, like 5 years ago or something?
I think they're starting to make new they're adding new equipment and making changes, Chris, because when we built the WR studios downtown, we at first, all of our incoming phone lines for on air are ISDN, and we had problems for the first year or so because the cable that brought them into the building, instead of putting it on fiber, the idiots put it up on copper, and that was a copper cable. First of all, it was old to begin with, but it went through 9/11, and I had a bunch of higher-ups at Verizon in the office at one point so we could figure out what the heck we were going to do with this and do about it. And they told me flat out, this was 5-6 years ago, they told me flat out ISDN was going away. And as soon as they started making changes and upgrading the central offices, we would probably be given a 90-day notice and go find something else, because ISDN, if they upgrade the equipment in the office, ISDN would not even be an option.
That's exactly what I was trying to find out, because I remember about 10 years ago talking with a couple of, back then it was about Atlantic, New York Telephone, and NYNEX in between. They had said, and I remember reading this, tariffs were being altered so that if you have pre-existing circuits, systems in place, they stay, you have to maintain them. However, if you're building new infrastructure, new facilities, you're not required to bring in the old or legacy technology, we'll call it. And that's what I've been noticing. Every time I've experienced issues with ISDN installations, brand new installations, I find out from the tech, I ask them, so has this central office been updated in the last 5 years? They're like, oh yeah, they redid it about 3 years ago and blah, blah, blah. I'm like, aha. So I think that's what we're seeing. We're now seeing the short tail of a long tail process that started probably 10 years ago, where now that the new places can be built because they can capitalize packet switch systems and DSLs and all the other stuff that's IP related. I think that they're using that as an excuse to get out. And also, AT&T is looking to get rid of all of their dial tone services and anything that is tariffed. They're trying to get their entire network to be packet switched. And I read a document recently. Part of that is because packet switch networks are not regulated by the FCC. Guess what that means?
And you know what? They probably aren't regulated by the state regulatory commissions either. And
no, they're not.
Exactly. We know what that means. That means there's, they're going to start doing what they want and damn the customer.
Well, yeah. And remember, there's no competition for them because the lobbying that their telecommunications industry does, the inability of politicians to get their act together, is giving them a pretty nice safe haven to operate within. And, DSL lines, because they run on the POTS line, the dial tone, get tariffed. Once that's no longer necessary, all that falls apart.
And
it's
Kirk brought something up. It said something before about the service techs and such. And well, Chris, when you were in the city doing things with CBS and other places, I'm sure over the last 5 or 10 years, you've seen the decline in the service techs. They'd walk in the door. I mean, they'd send techs over who knew dial tone or knew IP, but they knew nothing about ISDN. I mean, ISDN to them meant I sure don't know. And and
it's true.
I had a guy.
Oh,
it wasn't dial tone. It was ISDN. He had no clue, but he went downstairs to the mainframe, found a broken wire, came upstairs, and I had already looked at the codec, and the codec, it was armed and ready. We already made a call before he came up, and it worked. And he said, "Well, I don't know if it works." I said, "Yeah, it does." He goes, "Well, how do you test it?" I showed him the box. Well, yeah, but how do you know? I says, "I can connect to somebody. That's why didn't they send you with an ISDN test set?" He says, "I'm an IP tech." I don't know anything about ISDN, and we usually wait 3 or 4 days nowadays if you make a phone call and call for service, because nobody knows it. They have to wait till the guy gets freed up. It's scary.
Yeah, the industry is shifting. I mean, they're getting away from it because there's no money to be made in it. ISDN services doesn't make money. It costs them more to maintain it, install it, than it does an IP. I'll just call it an IP drop, whether it's DSL, whatever method they use. That's what it's come down to.
Right, and the article I wrote today for Talkers Magazine also mentioned things, in addition to things like ISDN going away. I mean, the phone company trying to save money and trying to make things more efficient, and in a way, you can't blame them. When they run a dial tone to your house, I mean, they go from the central office, they go to your house. There are 300, 500 houses between you and the phone company. That's a big fat cable that has to, expensive copper cable that has to be on the line. So they've gone to these slicks where they bring a fiber out. The only problem is when power goes out, you got about 4 hours on those batteries, and all of a sudden you have no phone service. Well, what if you need to call 911?
Those services aren't tariffed the same way anymore.
Right, and it's I mean, maybe they should tell the public that because people are used to a certain level of service, and that's not going to be the case anymore.
Well, that's part of the problem. We have an expectation that's no longer being met, but we have nobody maintaining that expectation through regulatory channels. Remember, fiber was being deployed by Verizon for the longest time for FiOS. Then they stopped because the stockholders said they didn't want to do it anymore. They didn't feel it was any value to it. So let's go back to ISDN. Is there value there? No. T1s? No. So Verizon not looking to save money. They're just looking to improve their stockholder value. And at the end of the day, that's what they're trying to drive. So is AT&T, which is SBC, and a few others. And that's what's driving all of this. So unless there's an actual public outcry through the politicians or through the regulatory channels, they will continue on this path, and we're going to see digital services disappear probably in less than 5 years. Maybe.
And we could spend a whole show on that, but I've really got to move on to the subject matter that we were going to get to. And that subject matter is this: unless a miracle happens, as Einstein put it, we have to deal with the world of switched packet networks. And as engineers, we got to figure out, okay, how are we going to do that? Yeah, we may be able to cry and scream and get petitions signed on this and keep ISDN going for a few more years. Maybe so. And that's fine if we can. ISDN is a perfectly good technology. But I want to point out a couple things about ISDN. If you are using ISDN for a radio remote broadcast, you're absolutely positively, unless you buy equipment that will handle several ISDN lines, you're limited to 128 kilobits, period. You can't do 384 kilobits unless you buy gear that's designed to, incorporate 2 or 3 or 4 ISDN lines and bundle them together. And that equipment exists, but most people don't use it. That's not what most broadcasters use. And if you use IP, you're not limited by that. You may be limited to less. You may be limited to a whole lot more, depending on what you're willing to pay for with the IP connection. The other thing is that if you go to let's say a sports venue to do a broadcast with ISDN, and you order an ISDN line, chances are you're going to order what you need, one ISDN line. Maybe in some cases, for something really important, you'd order a backup ISDN line. But it's going to come from the same provider. It's going to come out of the same cabinet full of gear in the basement somewhere with the rats. it's going to go through the same infrastructure. But if you go to a venue planning on using some installed internet connection, some IP connectivity, you may very well be able to get a second bunch of IP connectivity from another provider. You may be able to bring along some IP connectivity that's provided to you via LTE or WiMAX, RF-wise. You may be able to use some installed Wi-Fi at that facility. Okay, I realize the bandwidth may go up and down with use and so forth. My point is, you do have options in a lot of cases. You could even use satellite IP connectivity. That exists and will. And I've even heard that that you can get higher and higher bandwidths now than you could a few years ago. So there are more options, generally speaking, with IP than there are with ISDN, which tends to be limited to the incumbent telco. And even if it's sold by somebody else too, they're reselling the incumbent telco services. So let's get into okay, let's assume we're going to move into a world at some point where we have to use packetized switched services. And what are the goals we're trying to achieve, and how are we going to get there? And for the typical case, I'm going to assume a couple things that for doing a radio remote broadcast, we want low latency. We don't want to have buffers any bigger than they have to be. And I want to point out that, every night in the US, millions of people watch movies on Netflix and Hulu and, from other various providers. But a few months ago, somebody said Netflix accounted for a third of the internet traffic in the US in the evening hours. And Netflix movies are pretty reasonably reliable, at least here at my house they are. We've watched 2 or 3 at a time sometimes. We rarely have stuttering or problems or stoppages with Netflix movies. One reason is we're buffering up a number of seconds of video in the player, whether it's a Roku or an Apple TV player or the software that's built into the Samsung TV across my office. We get to have the benefit of time to ask and ask and ask again for the packet that's missing, so we can insert that packet into the buffering stream before it gets if it has to be decoded and go out to the TV set. We have time on our side. If you listen to a streaming radio station, chances are really good that it's buffering anywhere from 4 seconds to a minute. Typically 10 to 20 seconds worth of audio packets get buffered into the player's buffer. And so we got time to get that audio right. So time can really heal wounds in the streaming experience. But if we're doing a live remote broadcast, especially if we want to have a two-way conversation with people somewhere else, like callers who are coming into a phone system at the studio or other reporters at other venues that we want to have a conversation with, we don't have time for buffering. We have got to keep the buffering as low as possible. We got to be on the hairy edge of this working or not working. The other thing we want to do is we do want to use the highest coding bit rate that we can to get the best quality. I was talking to an engineer out in California a couple of months ago, and he wrote an article that appeared in the Broadcaster's Desktop Reference. The website is thebdr.net. And they used to use ISDN codecs to do music concerts, and they had trouble getting reliable ISDN lines after a time. So they started using an IP codec, and they were calling me because they were having a little bit of problem with the Telos Zip1 IP codec, and it turned out that they didn't actually need low latency. They were willing to put up with some extra buffering, but they were on WiMAX there. It was a rather tough situation, and they were just able to increase the buffering up to about 4 or 5 seconds, and they had a whole weekend of AAC coded audio at 384 kilobits per second. Way better quality. I say way better. They could tell a difference between the AAC at 128 on the ISDN line and the AAC at 384 kilobits per second coming over the IP codec, even though it was over WiMAX, and the extra jitter and drop packets made it necessary to have a bigger buffer there. Point is that with IP services, you as the consumer, you as the people ordering the service, you may very well, and you should have a choice of how big a pipe you're going to buy. Here at my house, I could get, a DSL circuit, that's a couple megs down and 256K up. I could do that.
but I'm paying for Comcast cable internet, and I'm getting 30 megs down and 4 to 6 megs up. Is it always perfect? No. Are we doing the Skype show right now? And when there's a problem, it's pretty apparent. There's a lost packet, or Skype decides to buckle down to a lower bit rate. Point is, you got some choices. Now, back to the question at hand, which is, okay, what can we do? What are the challenges when doing a remote broadcast? Again, you guys feel free to just jump at any time, but I'm just gonna read verbatim a few things that I wrote when I was really thinking about this. Let's see. When we encode data packets, we have to hand those. If we're doing a remote broadcast, we have to hand those packets over to a third party, and we hope and pray that the internet or our private WAN, whatever it may be, does its job and gets those packets to where they're supposed to go quickly and cleanly. We want to get the packets there fast, reliable, low jitter. If there's differences in latency of how long it takes a packet to get from point A to point B, we have to have a buffer at the receive end that's big enough to accommodate that jitter. Something else that's really helpful to do, if we're going over a network that we suspect is occasionally going to drop a packet, and the internet can drop packets. That was one of the rules of TCP/IP, that packets can be dropped and re-requested. Of course, with real-time audio, you usually don't have time to re-request this. We're trying to be as low latency as possible. So if we can't re-request a drop packet, what we need are codecs that have error concealment, that can actually put up with 2%, 3%, 5%, maybe even 10% missing packets, and the codec still produces audio that is reasonably pleasing to the ear. It's not all torn up and full of glitches. It may not sound perfect, but yeah, it's listenable, okay? And that's what companies like Fraunhofer have been working on to make codecs that have error concealment. Is it perfect? No. But does it do a job that's helpful and useful? Absolutely. In my paper here, I talk about some of the approaches to reliable IP audio. And the first approach is kind of tongue-in-cheek. You guys will get this. The best way to solve problems with IP audio, getting audio from here to there, low latency, is to simply use a perfect IP network. It works every time.
Do they exist?
Well, think about it. I'm sure at Musicam, certainly at Telos, we test stuff all the time on our own internal networks. And guess what? They work.
It works.
It works.
Absolutely.
Every packet we send gets to where it's going. It may be just across the hall. It may be across the office. It may be on the second floor. But every packet gets where it's going. There's no discernible packet loss, right? Local network. In fact, that's the basis of your local IP-based audio consoles, whether it's Wheatstone or whether it's Axial Livewire. We depend on every single packet being deterministic and getting where it's going on time. That's why we use high-quality switches like Cisco's, and that's why the whole network infrastructure is known and can be relied upon. The problem becomes, of course, when you hand your packets off to a third party and expect them to get where they're going to go in a timely fashion. Okay, so one way, use a perfect IP network. Now, let's imagine that you are Clear Channel, and you have a nationwide private wide area network because you can afford to do this with all your stations. And you want to go do a broadcast from a football stadium. Well, maybe you can ask your provider to extend that WAN connection out to the football stadium. Now, the football stadium is on your private WAN. You're not, if you are on some same facilities as general public internet services, you're given QoS and via the MPLS multi-packet label switching standard. You're given priorities such that you can pretty well rely on a packet that you stick in at one end of the WAN will come out the other end where and when it's supposed to. That's part of the whole idea of a private WAN with quality of service controls. So when I say use a perfect network, well, okay, that could be almost perfect. Very little mitigation would be needed there, unless you're overloading, some point in there. So that's one way. Use a perfect network, tongue in cheek. Second way, generate and receive fully redundant IP streams and send them over to providers. Now, so here's several scenarios. Imagine you're doing a remote broadcast at the Ford dealer, and you've got an IP codec. Instead of just sending out one stream and hoping that gets through the internet and over to where it's supposed to go back at the studio where it's decoded. Send 2 streams. Surely 2 streams, if there's a packet drop in one stream, the other stream won't get dropped, and your decoder can look at both streams and there's a packet missing here. Let's look at the other stream. Oh, there it is right there. We'll pick that one up and replace it, and there you go. Of course, if you just have one internet service provider at the Ford dealer, then sending 2 streams doesn't necessarily solve your problem. If you it could drop one packet from stream A and not drop it from stream B. That's certainly possible. You may exacerbate your problem if you've got limited bandwidth and now you're sending double the bandwidth just to hope that one of them gets through all the time. So that's kind of a problem there. Obviously, the right way to do this is to use 2 different internet service providers who hopefully are using 2 different internet backbones, and you do this at both ends of this connection. If you do that, then you really increase your chances of never missing a packet. 2 fully independent, redundant IP audio streams going through 2 totally different paths. Maybe one's DSL, one's cable modem, maybe one's LTE, one's cable, the other's cable modem, and hopefully you're going through different internet backbone providers. Maybe one of them's level 3 and the other one is, I don't know who other providers are. And at the other end, again, you've got diversity there too. So that is the basis of, if I'm not mistaken, APT. They have what they call SureStream technology, and SureStream will send 2 totally redundant streams, give it to you out of 2 physically diverse ports, and it's up to you to provide diversity in the pathing between point A and point B. Is that right?
Yeah, that's correct. That's correct.
Okay,
but I think broadcasters, I think we're missing a lot. We're trying to sort of fix an illness that doesn't really exist per se. I think we're forgetting that the ISDNs, T1s, Switch 56s of the day were tariffed and based on certain criteria that we required, or the phone company, or I should say industry required, in order to make things happen from point A to point B. When we migrated to IP, nobody carried over that same thinking and built it into the requirements of these providers. We should be really looking more toward forcing that hand, because you can have, I've done it, you can have 3-4 different carriers of IP at a location and still have issues trying to make things stable, from your remote back to the studio. I think we as an industry need to start pushing the buttons and say, hey, you know what, Verizon, AT&T, Sprint, TowerStream, and everybody else providing IP, we need to, come up with a plan that says, okay, I'm going to spend, because I've been ordering DSL dry pair for remotes for years, and they work like a champ. I never had any issues, and it was like believable until the day Verizon decided they were no longer going to support it the same way they were doing ISDNs and everything else at that particular CO and areas, and all of a sudden it became unstable. But I had no recourse, because there's no way for me to file a complaint to say, hey, I'm not getting my packets like they should, because there's no SLA, there's no nothing. But if it was an ISDN, as you pointed out earlier, hey, I can get a BERT test going. I can demand, because the tariff says you need to provide this point to point. And I think we as an industry need to start thinking that way and say, hey, wait a minute, you're going to provide this service to this industry for this purpose? We need to have a certain set of rules, something that says, okay, here's the boundaries we were going to work in. Otherwise, we're going to be chasing our tails like crazy trying to figure out how to make up lost packets because the guy in the middle doesn't have to do squat.
And
you know what?
And
30 megabits. I don't care. I don't want 30 megabits. I want 5. I want 5 in a properly managed network, so that I know the jitter and everything else is where it should be.
But I suspect
no one's doing that.
See, right now we're in the bad old days of internet network management. Don't you think that over time this is very likely to get better, as long as there are business demands? If businesses are willing to pay for better network management and better reliability, don't you think there are companies that are willing to provide that and get paid for it for doing that?
No, it's not going to happen, because most applications, and again, broadcasters wind up being that small little demand portion of the other business that's bigger. And what's going to happen is you're going to have third parties working with the phone company to allegedly provide you managed networks. The reality is they're not really managed per se for what we do. They're managed for telepresence, teleconferencing, web browsing, some other stuff that all of us do and use, but really...
All right, so what if the broadcast industry is not big enough to do this? Think about this for a second. What made home consumer routers get better in the last 5 years? gamers. Gamers demanded low latency so they could shoot the guy around the corner.
Yeah.
And so
you still have networks that can't provide the proper
the routers that you buy for your home are now better because of the online shoot 'em up gaming industry. Well, I'm telling you that I believe that down the road, hospitals, medical telepresence is going to require better and better facilities, and they're going to pay for it. And I think that just as with many other technologies, broadcasters are going to get to ride along with the demands of other industries that are bigger than broadcasting and get some benefit from that. Am I smoking something?
No. I mean, there is going to be a time when things like this will improve, but I think if we don't have some pushback, or at least somebody, I'll call it oversight, making sure that course is taken, we will be at the mercy of the hospital industry, we'll call it, or healthcare and stuff, and what they decide is what they want, or other people's demands, like like a Cisco switch over that of an HP switch or some Netgear or whatever. You need to sort of say, hey, I want to know, I want a DSL line that's going to give me equivalent or close to what I'm accustomed to with a frame switched or what do you call it, circuit switched system. Okay, so I have to spend say $100 to get installed rather than $39.99 because that's it's the retail price. Let's do it. Let's work with people to do these things. And the problem is there's no ruling that says they have to. And that's what I think is going to cause a lot of grief for us. And whether you're a small station or a large station,
there's no rule that a company had to come up with a car like a Bentley, and yet people were willing to pay for it, and a company was willing to make it.
Mm-hmm.
I mean, there's no government agency saying we must build very high-end cars with beautiful inlaid wood paneling.
No, the government industry is just basically saying it has to be low emissions, and you can't do this, that, and the other. So it's a different form. It's not a paneled interior.
Yeah. Well, we have had these discussions before, and I know it's difficult. I know it's tough, and yeah, we can keep applying. I don't know if the radio industry sure can't apply enough pressure to Verizon or AT&T to get them to do what we want them to do, but other industries, I believe, can that we can glom onto. I'm
just saying we should be looking at more like, how do I talk with my local carrier to find a way to ensure that my packet loss will be minimal, or jitter, or maybe work with them like we used to do years ago with the equalized lines, and work with the techs to sort of tweak out that little extra 15 kilohertz or 8 kilohertz circuit.
Yeah. Back when radio broadcasting was the only thing on the dial, it was important that they provide equalized lines. But do they care anymore? No.
Oh, no. I know that. No. But I'm saying with the DSL stuff, with IP.
Back to the countdown here. Okay, use perfect IP networks. Yeah, that works every time. Generate fully redundant IP streams and send them over two completely diverse paths. That works too. Here's another idea. Generate temporally diverse redundant IP streams. And so you have two IP streams, but one is delayed behind the other by some number of milliseconds. Okay? So you have stream A, and then you have stream A prime, and stream A prime is delayed. Let's say that you might expect on a given path, and this is where you have to characterize the path. Upload speed, download speed. That's just the beginning of it. There's many more things that you have to characterize over time about your path from point A to point B. And of course, the screwy thing about the internet is you might get a different path every time for different packets too. So what if you could generate stream A and stream A prime, and one's just behind the other? So let's say that stream A prime is getting every 150th packet dropped by some router along the way. Well, there's stream A prime coming along, and maybe it's also getting every 150th packet dropped, but it's a different packet. So the decode at the receive end, you need to increase the size of the buffer by the amount of temporal or time diversity between the two. But guess what? There's a second stream there, even over the same provider. Sure, if the provider goes out altogether, then you're your host. I get that. But even on the same provider, two streams with temporal diversity could be advantageous. And two streams with time diversity over two different providers could be even more advantageous. Got this idea actually from another IP codec manufacturer, actually from a customer of another manufacturer. They said they were having some trouble with a particular link, and some packets were getting dropped. And so they had plenty of bandwidth, but the link somehow was dropping some packets. I don't know if they ever solved the real problem, but they added a second stream, temporally diverse, a little bit delayed, increased the buffer time at the receive end by an equal amount. I don't know. Let's say it was 50 milliseconds. So they added 50 milliseconds to the already 200 milliseconds of delay that was going on. And guess what? Their problems went away because they were capturing enough packets in a reasonable amount of time from the second stream, A prime, in order to come up with a whole stream. So temporal diversity. And you know what? HD radio uses temporal diversity, doesn't it? They have data spread across, a little bit different than packet. It's not packetized, but they have data spread across time. So if you drive under a tree or a bridge or get a little blip in the data, the same data is going to be there a couple of seconds later. Yeah. Of course, you have a grand total of 8 or 9 seconds of delay with HD radio. We really can't stand for that in a live remote broadcast. All right. Any ideas on the temporal diversity? Can solve some problems in some situations?
That could definitely help. Yeah, I think that definitely has some merit. Makes total sense because that momentary loss of packet is because of a momentary hit to that link. If you're behind it with another set of packets by, say, 50 milliseconds, momentary loss, this one passes through, you get recovery. Yeah, that makes total sense.
Now, I should point out,
one of the reasons why you see that same principle is used in a lot of wireless co-FDM multi-carrier transmissions.
Yeah. So I should point out that, when we're talking about IP audio transmission from one point to another, generally this is not done with TCP/IP. This is done with UDP. We send a packet to where it's supposed to go. There may be things about the link that are set up with TCP/IP, but the actual audio streams are typically UDP. That means there's no handshaking going on. There may be a separate handshake that says, hey, buddy, I'm going to send you a stream. Okay, yeah, okay. Got your IP address? Yeah, I got the IP address. Okay, I'm going to start sending it now. Here it comes. And typically to reduce the latency, we don't have time for TCP/IP. We have time to send a continuous stream to where it's supposed to go, but then we can check up on the quality of the data, and we can check up on that on a separate side chain, if you will, with TCP/IP. So I know we talked earlier about, okay, if you're watching Netflix, that's TCP/IP. We ask for some data, we get the data, we handshake back. Hey, I got all of that except this one. Can you send that one again? But with low latency, especially a low latency two-way connection, where we need to try to carry on a conversation like we're doing here on Skype, typically this is sent UDP. There's no handshaking going on. If a packet gets dropped, it's dropped. We need to have an error concealing codec, or we need to have a second stream, a second source of recovering that lost packet. So here's another idea. Forward error correction. Now, FEC is employed quite a bit in other industries or other stream technologies. So, for example, if you are the proud owner of or a proud administrator of a satellite receiver at your radio station, you probably have noticed that there is a setup menu in there for FEC, forward error correction, and you have to set that setting for exactly what is being transmitted over the satellite channel. And you guys might be able to jump in here and help me if I'm misunderstanding this, but the way forward error correction works, it's a great technology if we're talking about replacing a missed bit or maybe even a missed byte here and there. So yes, we have a little impulse noise on the satellite channel, or we miss a 1 or a 0 on the fiber link or on the copper link. Not a packet, mind you, but just an individual bit or byte. With forward error correction, we're sending along parity bits for every, let's say we have 7/8 forward error correction, or do you call it 8/7? Anyway, for every 7 bits of data, we send a parity bit. So if we lose one of those 7, we know we can look at the parity bit and see what that one lost should have been. And you can go, so you develop some overhead. You have to have overhead to send the parity or the forward error correction. And there are different, pretty sophisticated means for doing this. They're smart, but we still increase our bandwidth usage. Do we increase it somewhere between 5 or 10% and all the way up to essentially doubling our bandwidth usage? If you're sending bits and bytes, forward error correction works pretty well. But with IP, if you drop something, you're not going to drop part of a packet and recover the rest of it. You're going to drop the whole packet. If part of the packet is unreadable, the whole packet's unreadable, generally speaking. So forward error correction in a packet-based system where every packet is chock full of data, it's a lot more. You almost might as well send the stream twice. Chris or Tom, any comments about forward error correction on a packet-based system?
Yeah, that would be true. I mean, forward error correction will send, I think it's like 3 bits, 3 of the same bits, 8 times or something like that. So there's a mathematical algorithm. I mean, forward error correction is handy if you're doing one-way STL links. That's where you can really put it to use. But it definitely has overhead, and it definitely can give you some issues. I shouldn't say in a negative way. It induces latency that you can control, but you have to be willing to accept it. But yeah, forward error correction is definitely handy. But in satellite links, satellite receivers, yeah, that's a big thing. You definitely need it there. But that's a one-way link.
But remember, with satellite packet-based transmission, I don't think forward error correction is not so helpful. But if you're talking about like the older systems that were not packet-based for satellite transmission, you're receiving a bit stream, not a packet stream. Again, if you lose if you lose a little bit of a packet, you've lost the whole packet. You've lost 1,500 bytes of data.
Yeah,
and yes, there are schemes for forward error correction over packetized networks, and there are some pretty sophisticated. If you Google that, forward error correction for packetized streaming video, for example, there are some proposals out there, and they're pretty complex. Not that complex can't be done, but maybe more complex than we actually need, and the benefit starts to look questionable. Again, it depends on the nature of your losses. If you lose one packet every 10 minutes, hey, forward error correction might be great, but it might cost you another, an additional 20 or 30 or 40% in bandwidth. And part of my thinking isn't bandwidth the problem anyway? I mean, if we
not
have
all the time.
No, not all the time. I get that, but sometimes bandwidth is the problem. If we're trying to use 200 kilobits per second of a 256 kilobit per second circuit, then we may occasionally have some problems. And if we drop our codec down to 64 kilobits per second, then we don't have a bandwidth problem. We still may have jitter, we still may have drop packets, but we no longer have a bandwidth problem. So FEC, I kind of blow off FEC as not a real practical solution for IP audio transmission. Although, keep an eye on it. So the last method that I want to discuss, excuse me, is one that I'm fairly familiar with because this is what the folks at Fraunhofer and Telos have worked together with quite a bit. And it has some problems of its own, but it can solve some issues. And that is when you have a dynamically controlled link, A to B, a dynamically controlled, and the link's not dynamically controlled, but the data we're trying to shove through it is dynamically controlled. So if you have an error concealing codec, number one, so you can stand to drop a packet here and there and it won't be a disaster on the air, then you have the ability to adjust the size of the buffer dynamically. Now, yes, if it's a big jump, you can get a skip ahead or a skip back in time with your stream. So you might be listening to a sports broadcast and the guy would say, he's at the 30, he's at the 20, he's at the touchdown. In other words, you miss where he said he's at the 10. It's possible to have that if your buffer's going to jump around a lot. The guys at Fraunhofer, and hey, most of the IP codec manufacturers use products from Fraunhofer, the AAC codecs and those families. It's possible to elasticize this buffer to some degree so that you can have little changes that occur in the buffer size and you don't really notice it on the air. There are some techniques to do that. So anyway, I'll leave it at that. The other thing you can do is while you're sending the UDP data, once or twice a second, you can also send some TCP acknowledgments back and forth. And you can say, how's your buffer doing at the other end? Is it okay? Are you consistently not getting all the data I'm sending? Well, then tell you what, after enough determination of the bad quality of the link, let's reduce the data rate. Let's go from 192 kilobit per second AAC. We're going to hop it down to 160 kilobit per second AAC and see how that goes. And so on the fly, both ends agree to skip down to 160 kilobit per second AAC. And so now you're using less bandwidth. Fewer packets have to get through in order to make audio at the other end. You may even have a system where, let's say that let's say your link becomes pretty crummy during your broadcast, and you get down to 90 kilobits per second AAC, and you still need to go lower. Well, then let's really switch gears and use a different algorithm. Let's go to high efficiency AAC, where we're going to use spectral band replication, but we can easily get our audio down in the 64 to 96 kilobit per second range and have perfectly good voice quality audio, not bad music either. So we have a system that will change gears on the fly. And, if you've programmed it to always try to do the AAC at a higher bit rate, it'll try that. It'll say, you know what? We've been going along for 5 minutes here, and everything's hunky-dory. Why don't we try to shift back up a little bit and see how it goes? So if you have an intelligent, dynamically controlled system like that, that helps in certain situations. Not every situation, but in certain situations, it certainly can help. So I think I've gone over all of them in my paper here. The perfect network, the dual redundancy, the time diversity, the forward error correction, and the dynamically controlled streaming. Which of those might be right for you? If you're doing a full-time STL and all of your program, not just remotes, but all your program material goes through this, you might not want a dynamically controlled system. You might not want something that is going to take a chance on moving around. You may just choose a lower bit rate. Oh, yeah, and I want to make a good point before I close this thing out. If you don't have if you don't have a dynamically controlled system, you pretty much have to do a couple things. You have to set your buffering at the receive end for the worst case scenario, the worst jitter case scenario. And you have to set your encoding, your bit rate, for the lowest throughput that you expect to have. So in both cases, let's say you're paying for, I'm going to use the case of a DSL line, a DSL that's supposed to give you an uplink of 750 kilobits per second. But there are times when you're not getting that. There are times when it may, for a couple of seconds, drop to 128, or even for a second, you're really getting nothing through, and then it jumps right back up. What if you have these dynamic conditions going on, which you often do? If there's other users, you certainly are going to have throughput variability. You have to provision your IP codec for the worst case scenario, and that's what you get to use all the time. And that's a situation that I think that technology needs to work on. Either you've got to get better IP connectivity where you can get something that's actually usable, 99.999% of the time, or you've got to have an IP codec that will adjust for the varying conditions so that you're always using most of or all of what you want to be able to use. So if I want to use 256 kilobit AAC, I get that all the time. But if rather than getting nothing through, if my available bandwidth drops below that, my codec will drop down and still give me audio, just not 256. Comments? I've yapped a while, haven't I? It's time for a drink.
That's okay. Well, no, I think the point's well taken, and what we need to learn in the industry and engineers like ourselves with IP now, I guess we've been so used to being able to get stuff we needed with the old-fashioned circuit switch. It was always handled by other people. Now in the world of IP, we are the phone company. We are the ones providing the quality of service, and we have to sort of pick and choose those tools. So as you pointed out, the codec is one element. That would be like the endpoints. Now what do we do in between? If we're going to rely on a third-party DSL, as you pointed out, do we now shop around and look for something with a SLA or some kind of quality of service? They offer that for business version compared to residential, blah, 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 that kind of thing. Or do we find a wireless solution that does IP, and then we can control even more of the factors of production and keep everything in check? Because I talked to a few of the customers. I've had a couple of customers now using these new wireless IP links between endpoints from their studio to various other studios and transmitter, and they love the fact that they control everything. That's it. They can dictate exactly the jitter, bandwidth, latency, whatever the network pipe is, and they put codecs on the other end, and off they go. So I think we need to retrain ourselves on how to go about checking this, finding a solution to the problem that we have, and just building on that. So your top 10 list there, so to speak, it definitely makes sense. You got to look at all the different factors, and then how do you apply them? Which one applies for my remote? Which one applies for my STL or my drop and insert between two studios back to the transmitter site? So
Chris,
I think it's an exciting time.
One thing I've noticed, Chris, when we have these discussions about IP and about the services available, you really seem to understand well the specifications that you want to have available to you. And you, you live more in this world than I do. I live in the world of mitigating what's available, and you live in the world of saying, "Yeah, but I want something better from the service provider."
Mind you, the reason I do this is because back when I was doing engineering for radio stations, I was getting pressured by the programming people. We need to do this. We want to be here. We want to be there. I'm like, well, I can't do it ISDN. Just not happening. And T1, forget it. So I had to start looking for other ways. And Tom will tell you, we did some stuff at his studios and, over IP. And people are like, you're doing what? How did you do that? I've done stuff, 7 years ago with IP stuff. People are like, what? What is this thing? It's like, don't worry, it works. So over time, I've honed the skill of understanding the little nuts and bolts, and you're right. But that's what I think people need to start getting into and understand. Like here, where I'm sitting right now in this building, I've done some IP stuff in this facility about 7 years ago, that people are like, what are you, nuts? What the heck? No, we're not doing that. Okay, here I am today. I talked to some of the guys downstairs and like, yeah, remember that thing? Yeah, we're doing it now. It's common practice. It's like, oh, okay, because they got past that hump of, I don't know, IP is not mature technology. I don't know if that's going to work. And then they looked at how they can manage it and go, oh, look, we can tame the tiger. Okay, fine. And then all of a sudden it works.
I got to liken this to some degree to back in the mid-'90s. I worked for Scott Studios, which then became DMARC, which then became Google, and then became Wide Orbit, right? Yes. Back in the days that I was there in the mid-'90s at Scott Studios, this was the bad old days of motherboard standards. We had 3 different bus standards: the ISA bus, the EISA bus, the just coming into the PCI bus. It was just horrible to try to find 2 things that would just freaking work together.
2? You're lucky you've got the one thing to work.
And so now, and not long after I left there at Scott Studios in the late '90s, I understand that it got better. I see my videos frozen. Sorry about that. Nothing I can do about that. Yeah, this is the great world of IP, right?
That's how it happens. Your buffering is in trouble.
Yeah. So those are really the bad old days. Nowadays, most any PC made will run a basic radio automation system pretty flawlessly. Oh, yeah, so we had the bad old days in the mid-'90s with these various standards that barely worked with each other. We take an ISA card from the company that made our audio card, and we plug that in the motherboard, and it would work in some motherboards and not work in others. And I mean the same motherboard, the same brand and model of motherboard. So
and then you changed operating systems.
Yeah. So it's getting it. A lot of this stuff works itself out and gets better. And there's for entrepreneurs, there's money to be made, hands to be held, education to be done during these times of transition. Hey, tell us, we got 20,000 ISDN codecs out there. Musicam's got thousands and thousands of them too. Maya and other companies. There's ISDN codecs all around the world, and now they're cutting off ISDN. Yeah, it's frustrating. It's an opportunity, but you know what? If you're an engineer and you're sitting on your laurels thinking, well, you're just going to complain about losing ISDN, I got news for you. Stuff's going to change all the time. Your kids will have different demands in 2 years than they have today. The fuel you put in your car is changing. Whether it's electricity or E85 or sunlight or biodiesel, it's changing. And man, we've just got to. I just say that we got to get on board with the change and work with it the best we can, and demand service out of people that provide it. We're paying for it. Here's what we want. But you may be just till you're blue in the face, and they may not change. You may have to deal with it the way it is.
Yeah, no, you're absolutely right. And I just, when I was saying earlier about demanding change service requirements and stuff like that, I wasn't trying to indicate that we should just do that solely. That should be part of the way you go about morphing into this new world we're in, or learning how to migrate to the new stuff. I was in a couple of meetings recently, about 3 weeks ago, with some, I'll call them engineering types, and the conversation of certain switch technologies was fading away, and they sat there with their arms crossed saying, this is not going to work, this is how it's going to have to be, and we're just going to have to find a solution. I'm sitting there going, I'll take sauerkraut and mustard with that hot dog, because if you keep thinking like that, that's where I'm going to meet you next. I was like, I couldn't believe some of the stubbornness that some of the folks in our business the techies are now exhibiting. It's like, and this recent ISDN articles and all this stuff, and Tom's contribution was great. It's like, wow, these guys are coming out of the grass, out of the weeds. These people that don't want to change. It's like, folks, like you pointed out, it's time to, start looking to the future.
There's you got to move along. Everything's going to change. Kirk is right. Things are going to change. Things are going to shift, and we have to kind of go with the flow. And
Tom, remember when you installed the Axia system at your facility back in the day? How much grief did you take when we did those tours of your place with folks coming through?
Oh gosh, with the HD radio stuff, oh my God. Yeah, and it's kind of here to stay. It's showing up in cars now. It's I mean, and that goes back to when the FM stereo came in. How many people laughed at people? Things do change.
It's just nowadays it moves faster than it did 10 years ago.
Right, exactly.
I do believe that we benefit from all these voices. One of the guys who is quoted in Radio World and maybe a couple other places too, Mike Simpson with Sports Backhaul Network. This guy's made a really smart business out of providing, out of taking the hassle out of ISDN ordering and providing radio stations. They walk in the door in the sports booth at NFL games, and there's their ISDN. They plug right into it, and by golly, it works, because Mike Simpson makes sure that it works. I applaud that, and Mike is just lambasting the fact that Verizon wants to kill ISDN off. I agree with Mike that ISDN's been reliable, and Mike's provided a fantastic service to broadcasters willing to pay for somebody else to go through the grief of having the ISDN. So Mike knows all about ISDN, what trouble you can have, and all that kind of stuff. But if Mike can, and by the way, I don't know Mike. I'd like to meet him sometime soon. I just know a little bit about his business.
I've talked to him. Good guy.
And had a conversation with him about him today with a major broadcast director of engineering, and got a really good report. And it would be interesting. I mean, what if the NFL went to Verizon and said, "Don't kill off ISDN. Our broadcasters need that. What are you, crazy? What's it going to take to keep it? We'll put ISDN from you, Verizon, or your assign in every market. Let's do it." I mean, you're the official communications company of the NFL. So it seems like a big voice like the NFL could carve out exceptions for this ISDN policy. But at some point, we're just putting off the inevitable. We're just whistling past the graveyard of ISDN. At some point, it's going to be IP. I just hope that the IP is that we don't go through just a horrible time with IP configuration and bad service and that kind of stuff, where we don't suffer too much. All right.
Well, I think broadcasters, if they stay on top of the folks migrating from our traditional circuit switch to the IP, say sporting arenas. If you're in a city like, say, New York City, with you have the New York Yankees, Mets have rebuilt their stadiums, and now it's completely IP. You can get ISDN, but you got to deal with a third party to bring it into their infrastructure. But working with them on several occasions, I know I've been able to do very reliable IP broadcasts from those venues. And I've talked to others around the country who have done the same. A couple of colleges I've worked with, that when they travel, they talk to the venue and they work with the IT guys and go, here's what we're doing, here's what I need. What is your system? How is your system designed? Is it carrier class, so to speak? Is it really robust, or is it just a ad hoc Wi-Fi spigot and there you go and good luck, whatever you get? I think if you go to that level and learn how to talk the language, you will definitely make this transition a little easier than just a shoot from the hip and hope that you hit your target, on the first try.
Yeah. All right, guys, we have gone well past our time, but I've enjoyed it, and thank you for. I mean, I know it's kind of up to me, and I appreciate you putting up with me doing this. But I gave you some of the points from my NAB paper. By the way, if you have a chance to come to the NAB to be in the room when mine is the first presentation on Sunday afternoon, 1:00 on the IP track.
You think so?
I have. Pardon me?
You think so?
I think so. Oh, I'm not the first?
Well, right now you're the first, but I'm the session moderator. This could change.
No. Well, Mr. Moderator, I have a demonstration that will occur in the room. Hopefully you won't object. And the demonstration, God, I want to keep it a surprise, but I just want to give you a taste. The demonstration will involve nearly 300 ping pong balls, and that's all I'll say.
Well, I have a demonstration too, and they'll be carrying the picket signs in during your thing. But anyway.
Oh, we're gonna have the big inflatable rat. You're gonna have the inflatable rat outside.
All right. So anyway, yeah. Well, obviously, hey, there's
somebody put up on the message board. Kirk Harnack, is he going to be nude? Oh, I hope not. I don't need to come back from NAB blind.
We don't need to start. We don't need to start NAB with jail time for Kirk.
Well, actually, that might be interesting.
God. All right, hey guys. Oh, you know what? We're not going to get paid unless I talk a little bit about our sponsor, right?
Absolutely.
I better do that. Let's see. I had it over here. Hang on a second. We can't stop that. Hey, if you've been watching the show, don't leave yet. Hang on. Let me tell you about something. I do want. We've talked about IP audio, and early in the show we talked about IP audio in the context of a local studio, like Livewire, like a system like WheatNet or like Ravenna. And there's finally a standard coming together that different proponents are working on, and Telos is one of the original proponents of this standard. It's part of the X192 project. So let me just tell you a couple things from the press release here. The chief science officer at the Telos Alliance, a fellow named Greg Shea. Greg is, oh my gosh, this guy is just a PhD level scientist. He's going to be looking at competing standards for IP audio studio networks. Now, this is not over the internet. This is for studio networks in a white paper called Taking the Sting Out of the Evolving Digital Audio Network. Greg is a co-inventor and a member of the R&D team instrumental in the development of Livewire. That's the IP audio networking technology introduced by Axia back 10 years ago in 2003. Greg is well qualified to discuss the future of networked studio systems, and he's also a member of the AES Task Group on audio over IP interoperability. It's a big word. And that's part of the X192 project. That was initiated by the AES Standards Committee to develop a high-performance streaming audio over IP interoperability standard. So anyway, Axia is a charter member of that and a sponsor of the X192 project. Greg says, you got to believe him, digital audio networking is here to stay. It's both the state of the art and it's the future. But with an AES standard for IP audio in the works right now, there's a bit of uncertainty about what the future will hold. Greg's presentation will look at both the differences and similarities of today's systems as well as equipment design issues such as network synchronization, stability, and design of local clocking hardware, stream formats, computing requirements, and more, with an eye toward helping broadcasters and vendors navigate these choppy waters and plan for the future. Greg is presenting his paper at the Broadcast Engineering Conference at NAB on Sunday, April 7th at 4:30 p.m. That's in the South Hall, room S227. That's the upstairs rooms that are above the overpass at the Las Vegas Convention Center. So I would really encourage you to check that out. If you can't be at NAB, stay tuned. We'll after it's over, we'll try to let you know where that paper would be available online. And I think it's going to be really interesting. It's great that there's an AES-sponsored project to bring these standards together, find common ground, and look for interoperability. So you could take a participating system. You could take a Lavo audio console and plug it into a Livewire system, or take some Livewire, some Axia gear, and plug it into a Ravenna IP audio network, and at least have the audio work. And, hey, standards might get all things like GPIO and things like that working. So interesting stuff. I'm glad we're at this point in technology, and I just can't wait to see where we're going to be in 2 or 3 or 5 years from now. So check that out. If you want information on that, go to axiaaudio.com. It's one of the headlines on that webpage at axiaaudio.com about Greg Shea's talk about the X192 standard. Guys, that's it. Any last comments before we go?
No, I'm good.
No, doing good. Man. Doing good.
All right. Thank you for not, throwing tomatoes at me today. I appreciate it.
Well, I did, and I got to clean my monitor off now. Come on.
Great comments in the chat room, and I tried to type a little bit, but I'm just not good at keeping up with that as Chris Tarr is. So I'm going to go back and read some of the comments later. I got to go. You guys do too. Thanks to Andrew Zarian for producing the show at the GFQ Network. Remember that you can subscribe to the podcast downloads if you can get audio or video downloads. You can also watch podcasts again. They're stored. You'll see all of them available through thisweekinradiotech.com, and you can also see them. They're posted sooner on the gfqnetwork.com website. You can also check out all the other interesting and fine podcasts from the GFQ Network. You're sure to find something fun and something offensive. You're going to love everything there at gfqnetwork.com. So, guys, thanks for being with us. Chris Tobin, appreciate you. Where can people reach you, Chris, at Musiccam USA?
Yeah. The emails have been coming through. You just you could email me there. You can call me if you'd like. I've had a few calls, so it's no problem there. And we get plenty of inquiries about how to do stuff nowadays since ISDN seems to be going by the wayside. So, but from the CBS Broadcast Center here in New York City, it's me.
Thank you for joining us from the Charles Osgood studio too.
Yes, the Osgood File. Make sure you tune in to your CBS radio stations across the nation, and Sunday morning on CBS.
And Tom Ray from Tom Ray, Consulting?
Broadcast Consulting. Jeez. No, it's Tom Ray Broadcast. TomRayConsulting.com is the website, and it's Tom Ray Broadcast Consulting is the name, and I'm not sitting in Charles Osgood's studio. But actually, I'll ask Chris, does he have a piano in that studio?
No, he doesn't. I knew you were going to ask. No.
Well, that was too bad because I had the pleasure of working with Charles a couple of times when I was at WTIC in Hartford, and he came in and we had this little piano. We had to wheel it in the studio, and he played live for us. And the guy, he's just a great guy. He really is. He was a lot of fun. So,
yeah.
Anyway,
he hosted holiday parties for the staff, and years ago you go to his house and it was piano time.
All right.
Anyway,
I'll see you all next week.
Yeah.
Chris, see if Charles in his spare time could write one of his famous poems for broadcast engineers.
Oh, yeah, that should be fun. I can try.
Probably answers you got to be kidding, but it'd be fun to ask anyway. All right, guys.
He's got a good sense.
Thanks again to Axie Audio. Oh, yeah, sorry. Stepping on you. It's this delay, There's so much we didn't cover. Gosh, we'll have to get to it. Okay, guys, talk to you later. We'll see you next week on This Week in Radio Tech. Bye-bye, everybody.
That's all the bandwidth we can pilfer this week. Another twit has propagated, and all the transmitters and audio equipment live happily ever after, thanks to the handsome engineer and his kind, benevolent care. We'll be back next week.
Lord willing and the creek don't rise.
This Week in Radio Tech. Subscribe to iTunes and you'll never miss a show. Search for This Week in Radio Tech in the iTunes Store. Soliciting is strictly encouraged. If you like today's show, tell a friend. If you didn't like it, we were never here. Kirk Harnack's wardrobe provided by the Salvation Army and the Red Cross Disaster Relief Services. Hair and makeup provided by Penelope Garcia Hernandez Weinberg.
He's unique, wouldn't you say?
I just want to get it over with.
This ends this transmission. Tango, Whiskey, India, Romeo, Tango. Signing off. Okay.